right, module 15. So we are going to start with using the rational roots theorem to find all zeros of a polynomial when the zeros are rational. So you have already actually seen this. Remember your rational roots theorem, our rational zeros, same thing, rational roots, rational zeros. Okay, so remember that we can find all of the zeros, all of the possible zeros as P over Q, where P is factors of the constant that's at the end of a polynomial, okay? And Q are factors of the leading coefficient. Okay? And then what we're going to do after that is once you have all of your candidates, okay, we test them to see which one actually is it, okay? So we're going to actually find all of the zeros. We're not just finding the possible ones. We're going to find all of them, okay? So in this example, we have h of x is 6x cubed minus 31x squared plus 4x plus 5. Okay, and they tell us that there's at least one rational zero. Okay, so let me just read real quick here what they want you to do here. Okay, I'm just looking here. Okay, so if you remember from Algebra 2, the degree of this polynomial is 3. That's right there, okay? So at most 3 zeros. Okay, and now we're going to make the list of all the possible ones. So P in this case is 5. So our factors are just going to be positive negative 1 and positive negative 5. Okay, Q is 6. So our factors of 6 are going to be positive negative 1, positive negative 6, positive negative 2, positive negative 3. Okay, so we have a lot of different possibilities here. All right. So our possible zeros would be, let's see here, all the p's over q's. So positive negative 1 over 1, positive negative 1 over 6, 1 over 2, 1 over 3, or positive negative 5 over 1, 5 over 6, 5 over 2, and 5 over 3. Okay, so they have, I'm just looking here quick. Okay, they do synthetic division to divide it out. I would much rather plug it in to see if it is a zero. Okay, if I plug it in, I get 0. So I think that I'm looking at the examples here quickly when I look at the and I just don't like it. So here's what we're going to do. We're going to start testing them. Okay, and I hope they don't give you this much to test when it's your turn to do it. But I would test the whole numbers first. Okay, so if I do h of 1, I'm going to get 6 times 1 cubed minus 31 times 1 plus 4 times 1 plus 5. So 1's the easiest one to do, right? So I'll have 6 minus 31 plus 4 plus 5. And all I need to know is that that's not 0. Okay, so 1 is not going to be a 0. I can test negative 1. Okay. And I'll have 6 times negative 1 cubed minus 31, this should be squared here, times negative 1 squared plus 4 times negative 1 plus 5. Okay. And I'm going to get negative 6 minus 31 minus 4 plus 5. And again, I can tell that's not 0. Okay, so I've eliminated 1. All right, now I'm going to move on to 5. Just it's easier, and I know actually it's going to work because I'm looking at the answer. So 6 times 5 cubed minus 31 times 5 squared plus 4 times 5 plus 5. Okay, and you wouldn't be able to use a calculator for this likely, so you're going to have to be able to do some of these little tougher calculations, but with 5 it's not so bad. 5 cubed is 125, so I'll have 6 times 125 minus 31 times 25 plus 4 times 5 plus 5. Okay, so 6 times 125, if you think about it, you can do 6 times 100, which would be 600, and then 6 times 25, which would be 150. So that's going to be 750 minus, okay, 31 times 25. I always think about when I multiply by 25 as if I have 31 quarters. Okay, so every 4 is $1. So I've got, if I have 31 quarters, right, 28 of them would give me $7. So I'd have 700. Okay, again, 28 quarters, give me 700, and then I'd have 3 more quarters, so 75. Okay, I need another decimal there. I'm having a brain fart. Just a second. Yeah, 775. I just wanted to make sure. Okay, and then plus 20 plus 5. So you might have to do some longer multiplication. And if you didn't follow that quarter thing, you can just do 31 times 25, the old-fashioned way, right? 1 times 5, 3 times 5, 1 times 2, 3 times 2. Sometimes you don't like to take the time to do it, but it's not that tough. Okay. All right, so 750 minus 775, I'll have negative 25 plus 20 plus 5. So that's 0. Okay, so out of my possible list of zeros, I get that 5 is a 0. Okay, now the good news is I don't have to keep factoring or keep trying to do more. I can factor. Okay, remember, if 5 is a 0, then x minus 5 is a root. And I can divide by x minus 5. This goes back to what we did in the previous module, right? Okay, once I found a 0, I found a root. Not a root, a factor. Okay, so I can factor it out by dividing. Okay, so I'm going to take my original expression and divide it by x minus 5. Again, I want to try to get to 6x cubed minus 31x squared plus 4x plus 5. Let me just double check. Yeah, okay. So then I know that I'm going to have a 6x squared here. And then I get 6x cubed and negative 30x squared. Now I need a negative x squared, which gives me an x here and a negative 5x here. Okay, and so then I need a 9x. Oh, what did I do wrong? Oh, that should be a negative. Right, to get the negative x squared, so that should be a positive 5. So this should be a negative x. There we go. Okay, and so then this is negative 1, and this is 5, and there's no remainder. Okay, and there should not be. There's never going to be a remainder. Okay, so now what I've done is I figured out that 6x cubed minus 31x squared plus 4x plus 5 can be written as x minus 5 times 6x squared minus x minus 1. Okay, and now I've gotten that down to a quadratic so I can factor it. All right, so now I can do x minus 5 times, what is this going to be? We'll have 6x and x. Let's see here. It's got to be, oh, I'm sorry, not 6x. 2x and 3x, and we'll have minus 1 and plus 1. And you can do that the old-fashioned way too. I guess I just did it the old-fashioned way. You can do it with the box method too. Okay. So once it's factored, now I have all of my zeros. So I have the x equals 5, which I already knew about. This one, if 2x minus 1 is 0, then 2x is 1, so x is 1/2. And for this one, x would be negative 1/3. And those are all on my list. Okay, the 1/2 and the 1/3. So there's my final answer with all of my zeros. Okay, so again, get your list of possible factors first. Start testing the ones that are the easiest till you get one that works. Okay, and that's what we did here. Once you get one that works, factor it out. Okay, and then get down to your quadratic that you can factor even more. All right, so there's a lot of steps there, so let me know if you need help with those. Let's look at the next one. The next one is when we have irrational zeros. Okay, so we are going to do, again, using the rational zeros theorem to find all zeros of a polynomial when we have irrational zeros. Okay, so in this example, we have h of x equals 3x to the 4th plus 8x cubed plus 2x squared minus 5x minus 2. And we are told that it has at least one rational zero. Okay, so we're going to find the other ones. So this one, again, it has at most 4 because it's a 4th degree polynomial. Okay, p is negative 2, q is positive 3. So our factors are negative 2, positive negative 1, positive negative 2. Well, this one's going to be a little bit easier. Positive negative 1 and positive negative 3 since they're both prime. Okay, so our list of possible zeros would be positive negative 1 over 1, positive negative 1 over 3, positive negative 2 over 1, and positive negative 2 over 3. Okay, so now I can start testing them. Okay, so next, if I do h of 1, I get 3 times 1 to the 4th plus 8 times 1 cubed plus 2 times 1 squared minus 5 times 1 minus 2. Okay, and that's not going to be 0, right? Because this is negative 7. It's going to be 6, so it's not 0. Okay, so now I'll try negative 1. So it'll be 3 times negative 1 to the 4th, so 3, plus 8 times negative 1 cubed, so negative 8. The odd powers are going to be negative here. So we'll have plus 2, plus 5, minus 2. And that looks to me like that is going to come out to be 0. So negative 1 is a 0. Okay, so I can factor it out. So x plus 1 is a factor. And I'll do my long division, x plus 1. Okay, to get to 3x to the 4th plus 8x cubed plus 2x squared minus 5x minus 2. So we'll have 3x cubed here. So we need a 5x cubed here. And remember, there's not going to be a remainder. So if I get a remainder, I know that I did something wrong. We'll need a negative 3x squared here. Okay, we'll need a negative 2x here. And that works. Okay, so now we have this is equal to x plus 1 times 3x cubed plus 5x squared minus 3x minus 2. Okay, now we keep checking our zeros, okay? We just have to keep, now we use this expression to check the zeros, okay? And so we're going to keep going here, and we're going to test 2. Because remember, we want to do the easy ones first, and that's going to be the whole numbers, okay? 2 cubed is 8. 8 times 3 is 24. 2 squared is 4. 4 times 5 is 20. Minus 6 minus 2. That's not going to be 0. Okay? And then I can test it with negative 2. Okay, so we're going to have negative 2 cubed will be negative 8. So negative 24 plus 20 plus 6 minus 2. That is 0. Okay, so that means that negative 2 is a 0. So x plus 2 is a factor. Okay, so we've gotten another factor that we can factor out. And we're just going to factor out of that second expression. Okay, so x plus 2 will factor out of the 3x cubed plus 5x squared minus 3x minus 2. And again, there won't be a remainder. Okay, so 3x cubed here, 3x squared here, 6x squared, and negative x squared. So negative x, negative 2x, negative x, negative 1, negative 2. No remainder. Okay, so now what I have is that original 3x to the 4th plus 8x cubed plus 2x squared minus 5x minus 2 is the same as x plus 1 times x plus 2 times 3x squared minus x minus 1. And I've gotten down to a quadratic, and I can factor it, or I can use the quadratic formula. And I know from the topic that I'm going to have to use the quadratic formula because it says I'm going to have some irrational zeros, okay? And remember, quadratic formula always works anyways. So if you're unsure, just use the quadratic formula, okay? So a is 3, b is negative 1, c is negative 1. So I have the opposite of b, plus or minus the square root, b squared minus 4ac all over 2a. So that's going to be the square root of 13, right? 4 times 3 times negative 1 will be a negative 12. 1 minus a negative 12 will be 13 and over 6. Okay, so that gives me my 2 other zeros with the plus and the minus. Okay, so all of my zeros, I have negative 1, I have negative 2, I have, they want you to split the numerator, it looks like in here. I would guess that they would accept it as written if you did 1 plus the square root of 13 over 6 and 1 minus the square root of 13 over 6. In their example, they do 1/6 plus the square root of 13 over 6. And they do 1/6 minus the square root of 13 over 6. Okay, so there's all your zeros. Okay, next one. All right, now we're getting into your imaginary numbers, if you remember those from Algebra 2, okay? We have multiplying expressions involving complex conjugates. Okay, so first of all, if you remember, I is the square root of negative 1. So I squared is negative 1. Okay, imaginary numbers have the real part a plus bi is the imaginary part. Okay, complex conjugates, it's called a complex number also. Actually, I'm going to write, it's not really imaginary. The BI part is, but we'll do complex numbers. Okay, so complex conjugates are pairs, A plus or minus BI. Okay, and when you multiply complex conjugates together, we get a real number. As long as they're complex conjugates like that. Okay, so the example that we have is x minus 6 plus 2i times x minus 6 minus 2i. Okay, so 6 plus 2i and 6 minus 2i, that pair together, they're called complex conjugates. Okay, what I would encourage you to do is an area model and distribute that negative. So we'd have x minus 6 minus 2i times x minus 6 plus 2i. Okay, and then when you make your area model, it'll be a 3 by 3. Okay, and you can fill it in. Just treat I as a variable for now. So x times x is x squared minus 6x 2xi. And it really doesn't matter what order you write those in. Negative 6x, positive 36, negative 12i, negative 2xi, positive 12i, and negative 4i squared. Okay, and what's going to happen here is anything with an I is going to disappear. Okay, the first way that it's going to disappear is opposites. So negative 2xi plus 2xi cancels out. And then we have another pair of opposites there, right? 12i minus 12i. Okay, and then for that negative 4i squared, there's nothing to cancel it out with, but that is actually a real number. Okay, negative 4i squared, remember I squared is negative 1. So it's negative 4 times negative 1, so it's positive 4. Okay, so what we have in the end then is x squared minus 6x minus 6x, so minus 12x, plus 36 plus 4, that 4i squared, which was 4. Okay, so plus 36 plus 4, so 40. Okay, and whenever you do these problems, you should get all real numbers then. Okay. All right, let's do another one. We have finding polynomials of a given degree with given zeros. And they tell us we're going to have complex zeros. Okay, so we have a polynomial f of x of degree 3 with zeros, 1 and 3 plus I. Okay, well, if it's degree 3, that means that we need 3 zeros. Okay, and they only give us 2 of them, right? But if you remember this from Algebra 2, oops, this should be an I. If 3 plus I is a 0, then 3 minus I is also a 0. If there's a complex 0 like that, then its conjugate also must be a 0. Okay, so what we need to do to get this polynomial is take the zeros to get the factors. So our zeros are 1, 3 plus I, and 3 minus I. So our factors will be x minus 1, x minus 3 plus I, and x minus 3 minus I. Okay, so our polynomial will be x minus 1 times x minus 3 plus I times x minus 3 minus I. Okay, so we can do the multiplication that we just did in the previous example, where we're going to distribute that negative. And we're going to multiply them together. And it's going to be easier if we multiply these two together first, because that's going to get us all of our real numbers. So x minus 3 minus I and x minus 3 plus I. Okay, so we'll have x squared minus 3x, and then we have ix minus 3x, 9, and minus 3I, minus ix plus 3I, and minus I squared. Okay, so when I do this, remember the 3 i's will cancel out. That's always going to have the same structure. So negative ix is going to cancel out. Negative I squared is negative 1, which is 1. So now I have x minus 1 times x squared minus 6x plus 9 plus 1, so plus 10. Okay, and now what I'm going to do is multiply those two together. So another area model. We're going to have x minus 1, and then x squared minus 6x plus 10. Okay, so x cubed, negative x squared, negative 6x squared, 6x, 10x, and negative 10. Okay, so I get x cubed minus 7x squared plus 16x minus 10. And that's my final answer for f of x. Okay. So easy to make one little mistake there. Okay, so just be really careful with your work. Next one, we've got using the rational zeros theorem to find all zeros of a polynomial with complex zeros. So we're going to go back to what we had here. Here we had rational zeros and irrational zeros. Start with rational. Oh. Okay, now we're going to do the same thing, but we are going to have complex zeros. Okay, so let me get back down here. So now we have using the rational zeros theorem to find all zeros of a polynomial. And we're going to do some complex zeros. So you might remember this from Algebra 2 also. When you use the quadratic formula and you got your imaginary numbers that you got into. Okay. And again, we're told that this expression that we're going to be using has at least one rational zero. So we can use the rational zeros theorem. Okay. So h of x is 2x to the fourth minus 10x cubed minus x squared plus 4x plus 5. So we're going to go through that same initial process. P is 5, Q is 2, so that gives us positive negative 1, positive negative 5, positive negative 1, positive negative 2. So our possible zeros would be positive negative 1 over 1, positive negative 1 over 2, positive negative 5 over 1, positive negative 5 over 2. Okay? We already know that we're going to have complex zeros, but remember those come in pairs. Okay, so if we have one complex zero, that means we have two complex zeros. Okay, and the fact that we have one rational zero, because it tells you that in the problem. Okay, so we're going to have one rational zero, two complex zeros. Okay, so that means that we have another zero, and it could be rational or irrational, but it's not going to be complex because the complex come in pairs. Okay, so the third one will either be rational or irrational. I'm sorry, the fourth one will either be rational or irrational. Okay. And just based on the type of problem, it's going to be likely rational, because otherwise it's going to be hard to find it. So I'm going to guess they're going to throw a rational one at you. Otherwise, it's not really a problem that you can do yet. Okay, so we're going to test our possible zeros. H of 1 will be 2 times 1 to the 4th minus 10 times 1 minus 1 plus 4 times 1 plus 5. So we've got 11 minus 11, so that is 0. So we got one already, okay? 1 is a 0, which means x minus 1 is a factor, and we can divide it out. So x minus 1, okay, and our goal is h of x, so 2x to the 4th minus 10x cubed minus x squared plus 4x plus 5. So 2x to the 4th. Okay, so 2x cubed minus 2x cubed. Okay, and then we'll have minus 8x cubed. So this will be negative 8x squared and 8x squared. Okay, and then I'm going to need a negative 9x squared. Okay, so negative 9x and 9x. I'm going to need a negative 5x, so negative 5 and 5. Okay, so now I've got h of x can be split into x minus 1, 2x cubed minus 8x squared minus 9x minus 5. Okay, now I'm going to try my other zeros that I have listed. So I can try a negative 1. Negative 1 cubed would be negative 1. Negative 1 squared would be positive 1. Negative 1, 5. So I'm going to have negative 2 minus 8 plus 9 minus 5. Okay, and I've got minus 15 plus 9. That's not 0. Okay. All right, I'm going to skip the 1/2 for now, and I'm going to move on to the 5 to test. So 2 times 5 cubed minus 8 times 5 squared minus 9 times 5 minus 5. So this is going to be 2 times 125, so 250. And then 8 times 25 is 200, right? 8 quarters is $2. Minus 45 minus 5. And hey, that works. 250 minus 200 is 50. Minus 45 minus 5, that's 0. Okay, so 5 is a 0, which means x minus 5 is a factor. Okay, so now I can divide further by x minus 5. Okay, so I'm going to scroll down here. And I'm going to do x minus 5 with a goal of 2x cubed minus 8x squared minus 9x minus 5. So 2x cubed would be a 2x squared here. Negative 10x squared. Okay, so then I need a 2x squared. So we'd have 2x. Negative 10x. We need an x. That's going to be 1 and minus 5. Okay, so now h of x is x minus 1, x minus 5, 2x squared plus 2x plus 1. Okay, so I found 2 of my zeros, so the 2 remaining ones must be my complex. Okay, so I'm going to do the quadratic formula. A equals 2, B equals 2, and C equals 1. Try something different here. Okay, so I got the opposite of B plus or minus the square root of B squared, which would be 4, minus 4AC all over 2A. Okay, so I'm going to have negative 2 plus or minus the square root of 4 minus 8, so negative 4 all over 4. Okay, and then this is where our imaginary numbers come in. Okay, so remember, I think they kind of assume that you remember this from Algebra 2 or whatever, that the square root of 4 is 2. The square root of negative 4 is 2i. Okay, so you do it the same as you would any other square root. You just put the I on it. So like when you do the square root of 50, right, you do that. It's the square root of 2 times the square root of 25. So you'd have 5 root 2. Okay, the square root of negative 50 is just going to be 5i square root of 2, or 5 square root of 2i. Okay, it doesn't really matter. Kind of depends on the textbook how you decide to write it. Okay, so we're going to have negative 2 plus or minus 2i over 4. Okay, and then like I said before, they have you split that up. So negative 2 over 4 plus or minus 2i over 4. And they want you to reduce that. So negative 1/2 plus or minus I over 2. Okay, so now we have all of our zeros. We have the original, I don't want a parenthesis there. The original ones that we came up with by testing. Okay, so we already have, the 1 and the 5, and then now we have the negative 1/2 plus I over 2, and the negative 1/2 minus I over 2. Ooh. Not sure if I like that pen or not. It's kind of fun. Okay. All right. Let's see here. I think I might stop the video there so I can start a clean one. Okay.